Hello and a warm welcome to Sarat Chandra IAS Academy, where your dreams are on mission. This is Yatharth here. Today we'll be talking about India's nuclear power program. We'll also see whether we have entered the stage 2 of our program, that is PFBR, the development of the prototype fast breeding reactors, how they are different from the pressurized heavy water reactors, which we are using in the stage 1. Alright, and what is the stage 3 of our nuclear program? Alright, so let's see a list of topics that we are going to cover. The first thing that we are going to cover is the timeline of India's nuclear program from the very basics till now. Next, we'll focus on why is it in news now in 2024 and how is it important for our prelims? What can be asked? Alright. Furthermore, we'll see what are PFBR or prototype fast breeding reactors and what is the meaning of all these terms, fast breeding reactors and so on, how they differ from the pressurized heavy water reactors or the stage 1 reactors. Alright, next thing we see how do they work, the working mechanism of the PFBR and why was PFBR delayed till now. Okay, why, what happened in the 1974 and 77? Okay, what happened in 2003? What happened, which agreement was signed between India and US in 2005 and what is happening in 2024. All right, what are the SMR, small modulation reactors? We'll be talking about these also. What is the significance of the stage 2 for India and what are the challenges involved for the future of development of India's nuclear program? All right, let's talk about this. So in 1948, right after India's independence, India was very quick to hold on to the atomic energy development. The Atomic Energy Act was passed. Atomic Energy Act was passed and Department of Atomic Energy, that is DEA, was established. In 1954, there was a very renowned physicist, Dr. Homi Jahangir Bhabha, HJB. So he was made the chairman or the first chairman of the DAE. So please remember, very, very important, first chairman of the DAE. Now, Homi Jahangir Baba was very familiar with the Indian situation. He knew that there is less natural uranium here in India, that is uranium 235 as well as 238, and more of thorium. Alright, so obviously he knew the fission reactions that can be carried out with uranium and how thorium can be used with the byproducts of the fission reaction of stage 1, those produce the plutonium. Alright, we'll be discussing all this. So he decided to envision a three-stage program for India. A three-stage program for India. So we'll be talking about the stage 1, stage 2 and stage 3. So what was the stage 1? That you utilize natural uranium in pressurized heavy water reactors. Basically developed the PHWRs. PHWRs to produce electricity. Now issue with these PHWR, they produce energy, yes, very good. Okay, they deplete the uranium. It cannot be used further and they produce some plutonium also, which is also radioactive. Okay, so for this the decisive solution was stage 2. Stage 2 was use this plutonium from the stage 1 in fast breeding reactors in FBR, fast breeding reactors, to produce more fission material. All right, and it stage 3 utilize thorium, which is abundant in India in breeder reactors for long term or sustainable nuclear energy. So this maybe we'll take next 10-20 years, God knows. But right now we are at stage 2. We have developed a prototype fast breeding reactor. All right, in 1956, the BARC was established. It was formerly known as the Trombay Atomic Research Center, and this was the primary facility for nuclear program of India. In 1960, India's first research reactor Apsara was born. Apsara. Okay. The next thing is 1969. So what happens in 1969? The Tarapur Atomic Power Station, which was first commercial. This was research, please remember, and this was commercial. The Tarapur nuclear power station 1 and 2 TAPS. This was in Maharashtra and it was commercial. That means electricity was being produced and sold to various discoms from here. In 1974, what happens? That India conducts its first powerful or peaceful nuclear test, that is Smiling Buddha in Pokhran of Rajasthan, that is also known as the Pokhran 1. Alright, this attracted sanctions from the West. They were not very happy with what India was doing in its backyard and implemented further sanctions. In the 1980s, India focused on the Indianization of the fuel. So, what happened? Uranium stopped coming from the West as well as from other countries, let's say France. So, this was critical for India's nuclear development, but it stopped coming. So, India was not very happy with this. So they had to use alternative fuels for the PWHRs. And in 1980s, India focused on the Indianization of nuclear fuel cycle technologies and reactor designs. All right, in 1998, then what happens? Pokhran 2 was conducted. So India has shown the world that regardless of the sanctions and all, we are still strong and will not deter from our nuclear development program. In 2005, India and US conducted or came to an agreement, also known as the 123 agreement, okay, which paved the way for India's further, and it ended most sanctions. In 2010, India continued to expand its nuclear power and refines its fast breeder reactor technology. Okay, it was we have been working on this FBR since 2003, and so even earlier. All right, now let's talk about the present and so on. But first of all, let's have a look on India's current most important nuclear power plants. The first one is the Rabatwata of Rajasthan. This is near Kota, also very famous for the coaching centers. Then there is Naroda in Uttar Pradesh, the Tarapur, the first one and the most famous. Then there is the Kakrapar in Gujarat. And the one in news, that is Kalapakkam in Tamil Nadu. This is where the first PFBR core loading has happened. Okay, this is why it's in news. And the Kundakulam, Tamil Nadu. This is also much in news because of the locals not being happy with the disposed waste coming from the nuclear power plant. All right, people are really unhappy with what's happening around here. So you can read it. It's issue for the people there. Okay, let's now talk about what's happening now in this news. So the PFBR core loading has happened. Where it has happened? In the Kalapakkam in Tamil Nadu. All right, in the Madras Atomic Power Station, Kalapakkam in Tamil Nadu. So let's just expand the PFBR. What is P? P is prototype. What is a prototype? Prototype is the first made thing that works. Then there is F. F means fast. And B means breeder or breeding. And R means reactor. So R is a normal term here. FB, we'll see later that what happens to the neutrons, that it's known as a fast breeding, and P is the first thing that it has been developed, that means PFBR. Alright, so it marks this core loading has happened. Okay, core loading means basically it has started working. It started working, or something that was implemented in its core and it has been loaded, so it started working, and this was witnessed by our Prime Minister Narendra Modi. This marks the start of the second stage, stage 2 of our nuclear development program, which was envisioned by Homi Jahangir Bhabha in 1954. Okay, after around 70 years, we are seeing this. All right, so this does a closed fuel cycle. It does a closed fuel cycle. That means the nuclear fuel is not supposed to supply more to this core. It uses the plutonium already produced by itself, all right, from various different materials. Okay, from on an oxide and a blanket material that we are not going to talk about right here. Second thing, a unique feature of this PFBR, it is cooled by sodium. It is cooled by liquid sodium, not by water. Okay, or by heavy water, unlike the stage 1 reactors. Okay, let's go further. So it's basically will help us in achieving self-reliance in the fuel supply for the future fast reactors. This is heavy water reactor, PHWR. So this is our stage 1 reactor. This is our stage 1 reactor. So what we see here is that this is the core of this reactor. These are the fuel assemblies. When we talk about the fuel assemblies, we essentially talk about the uranium. Okay, so these are uranium rods here. These are the pressure channels which pressurize the water here. Okay, and the neutrons basically react with this uranium. They emit energy as well as various different things. These are the fuel rods. Okay, water is pressurized so that does not boil. We'll talk about this as well. This is the cooling circuit and electricity generator and so on. The electricity that comes out, or the energy that comes out, let's say heats this water. Okay, and this water heater moves a turbine here. This is steam turbine here, and electricity is generated. Okay, basically works on the turbine method. So very simple. Next, we see the fuel that we are using. So I know it all looks a bit complicated, but we'll try to keep it as simple as possible. This is uranium 238, and this is the number of electrons and neutrons it has. Sorry, the proton and neutron it has in its own nucleus. All right, so basically we knowing about the structure of an atom, a simple atom. It has some orbitals, and there we can find the electrons. Then it has a nucleus where we find the neutrons as well as the protons. The protons have a positive charge, neutrons have zero charge. This is why they are called neutrons, and electrons have a negative charge. Alright, they have very small weight, the electrons, but protons and neutrons have a same weight. What happens when a nucleus is struck by an external neutron? It delivers some momentum to it. Alright, and there is always, if there is the atom is unstable, then it will always break down into two counterparts. So this is what happens in a fission reaction. This is what happens in a fission reactions. Okay, the opposite of this happens in a fusion reaction. So this releases energy, extra energy, and the opposite of this happens in a fusion reaction. For a fusion reaction to take place, that means for different atoms to merge into each other, let's say deuterium and tritium. All right, so what we need is very much temperature. This is a sign of temperature, and very much pressure we need. All right, so this often takes place at the surface of the sun. We can observe this, and the China is also making, let's say, artificial machine to do this. Okay, but we are not talking about the fusion here. We are just talking about the fission reaction that is taking place into the nuclear plants right now to produce electricity. The stage one nuclear reactions. All right. So what we see here is that uranium 235 is struck with a neutron. It produces uranium 236 because one neutron is added to it in its nucleus. All right, but it breaks down further into barium 144 and krypton 89. So we are left with one neutron that was initially struck, and two other neutrons are released. Okay, with this, some energy is also released. Okay, this is the energy we care about, and these are the neutrons which are further used into bombing the other uranium 235 molecules or atoms that are present in the fuel. Alright, so this can go on as a chain reaction also if not controlled. This is why we use the heavy water D2O. This D2O slows down these neutrons. Okay, and D2O also absorbs the heat that is produced, the temperature or the heat or energy that is produced. Okay, and which is what drives the turbine via the steam formation. Okay, now let's talk about the pressurized part. So the water is pressurized because we do not want the water to boil. As we can see, that water is just lying alongside the fuel rods or the uranium rods. Now, a lot of energy is released here. We all know this. Now, because of this energy going directly into water, the PHWR, the first stage reactors, do not use a direct steam thing. Alright, the steam is not directly produced by the boiling because we do not want the water to boil inside the reactor itself. Okay, if the water starts boiling here, our equation or our reaction will not be completed. All right, or it will go awry or clumsy. It can lead to a disaster if the water starts boiling here. All right, we want the water to be the same here. So what we do is that we apply some external pressure. Now let's say this is a container of water, and when we are going or making it boil, it will change into water vapor or gaseous phase. The distance between the water molecule will reduce. Okay, they will expand. So what we do is that we apply some pressure, external force. Pressure is equal to force upon area. Alright, so we apply some pressure in here to keep them close and bound into itself so that it does not boil. Okay, so now we have understood everything. One more thing that we need to understand is natural uranium. This natural uranium, whenever we get it as a fuel, so it has both the parts, uranium 238 as well as uranium 235. So we saw that which one we used in the PHWR. In the PHWR, we use uranium 235 and it got consumed. It got consumed. So now we are left with uranium 238 as well as plutonium. Plutonium. So we must use these somewhere to do something or make us more energy somehow. This is the basic of our stage 2. Okay, in the stage 2 we will be using Pu-239, that is plutonium 239 with the uranium 238. Okay, in the PFBR. So we need a different reactor for this. That is our prototype fast breeding reactor. PFBR to produce energy, plus uranium 233. Sorry, again a new type of uranium 233 and more plutonium 239. Okay, now as a basic premise, what we see that this uranium 239 can be used again in here. What we will be needing uranium 238 to carry on the reaction. Okay, so it will be basically producing more plutonium that it consumes originally, and all of these are connected. So for the establishment of this PFBR, the Indian government and the DEA set up a a special purpose vehicle we can say, or a basically research center. This is known as the Bharatiya Navikiya Vidyut Nigam Limited. That is, Navikiya means nucleus. Okay, so relating to nucleus to implement the stage 2. And this was established in year 2003. So after 21 years, this technology has come into action. Alright, in stage 3, what we will be doing? Plutonium 239, which we have here. This will be combined with thorium 232. Thorium 232. And this will produce a uranium 233. Alright, that will again we will use. Alright, here's an infographic that tells us about the 3 stage and how they are connected to each other. So this we saw that Homi Jahangir Bhabha envisioned India's nuclear power program in 3 stages in 1954. Alright, to suit the country's low uranium resource profile but also high thorium. High thorium. Alright, so what we see natural uranium, I already explained to you it as uranium 235 as well as 238. So 235 gets consumed in the stage 1 in the pressurized heavy water reactors, and we are left with uranium 238 for the PFBR. Okay, so what we see here, the depleted uranium and the plutonium we find here, uranium 238 and plutonium 239. Alright. Now we will introduce some thorium in the stage 2 and use this plutonium 239 and the depleted uranium 238 in the stage 2. So fueled by a mixture of plutonium and natural uranium with sufficient stocks, thorium is introduced to convert it into U-233. So again some energy is released in the stage 2 and we obtain U-233 further with the plutonium. So plutonium goes back into the stage 2 for the uses, and this U-233 now we'll have to develop another type of reactors, stage 3 reactors, that is U-233 fast breeder reactors. We are not here yet. Okay, we are still working on it. So thorium will be introduced in this U-233 to produce more energy. So mix of thorium and uranium fuels the reactors. Thorium transmutes to 233 which powers the reactors. Okay, so it is all and all a interplay or a game of uranium 238, 235. Okay, this is used in stage 1. This 238 is used in stage 2. And in stage 3 we will be using the uranium 233. Okay, and what are the other components that will be used? Thorium, that is thorium here, and plutonium 239. Okay, so this is all the game that we are going to play in stage 2 and 3 further. Okay, now let's talk about why was FPFBR delayed? Why it took us 21 years? Okay, why it took us 21 years to reach here? And why did we start in 2003 instead of 1970s? Okay, the simple answer is West was not happy with our doings, that India in its backyard is bombing nuclear things. So it was built, the Kalapakkam that is now in use, the PFBR, the prototype one. So this was built in the Kalapakkam earlier in Tamil Nadu only in 1977. Okay, but it was delayed by 26 years later on because of the sanctions that West put on us. Okay, France was about to deliver us enriched uranium. This was supposed to come from France, all right, but this was delayed and was rejected actually. Okay, and we had to use mixed carbide fuel. Now let us talk about this Operation Buddha as well. So this was also known as Pokhran 1. So Pokhran is a place in Rajasthan near Jaisalmer, in the Jaisalmer Jodhpur circle. All right, and it's a desert type of place in Jaisalmer, sort of desert type of place. So it's a very safe place to test any nuclear bombs. And India, this blasted a nuclear bomb, basically detonated a nuclear bomb in 1974 here. So this is known as the Pokhran Test 1 or Smiling Buddha mission. Okay, this happened because of the 1962 Indo-Chinese War and the Pakistan's ambition to develop a new nuclear bomb in the similar or same year. Now West felt sort of threatened with this and put sanctions on us. But in 2003, PFBR started developing again. It got a green light from the West mostly. All right, but what issue happened that most of the people who were working on PFBR by now, after 23 years, 26 years, they were all retired or nearing their retirement. So the consensus, the teamwork, and the technology was there was a brain drain, sort of, you can say. All right, the brain was getting out. Furthermore, what we see even after 2003, there were fund crunches. So this is what we are not going to discuss. It is like out of syllabus, but I have inculcated some points for you, which are most important for the PFBR as per the prelims. All right, the simple portion. Although I have tried to explain very well about all the stages and the nuclear reactions, still, if you feel it's very, very complicated, you can just skip most of the things and talk about this. All right, so PHWR, what we were talking in the stage 1, we talked about the PHWR, pressurized heavy water reactors. Okay, so they use pressurized water. I told you why. So the water does not boil inside the reactor, and heavy water is D2O. Okay, we already know that it uses low enriched uranium 238 as a fission material, and uses 235 also. It gets consumed completely in the stage 1. So we are left with some uranium 238, and we are also left with plutonium 239 as a byproduct. All right, so in stage 2, what we see in stage 2, so this is collected from here, the uranium 238 and plutonium 239, they get mixed in a core. Okay, so there is a core of the reactor. In the core of the reactor, what happens? We put in uranium 238 from the first stage, and we put plutonium 239 from the first stage into the core, and then they are reacted. Okay, so how can we say that more plutonium is produced? We need to mix something. Okay, so there the reaction will take a mixed oxide, a mixed oxide. So this is the thing that will supply the plutonium, more plutonium to this reaction. Okay, along with the blanket material. So we do not know what blanket material is there. It is a scientific technology. So what we see that more plutonium 239 will come out eventually. And if we have more plutonium 239, then we can just carry on the reaction again and again. So it is also known as a closed fuel reaction. A closed fuel reaction. Please remember this point. It is very, very important. Okay, second thing, what we saw that what is the fast breeding? What is the fast breeding? Fast breeding means neutrons are not slowed down in this. So again, second difference from the PHWR where the neutrons were slowed down with the use of D2O. So neutrons are not slowed down because D2O is not present here in the PFWR, PFBR, sorry. Okay, so what is present instead of the D2O? A liquid sodium, a liquid form of the sodium, liquid Na. Sodium also known as natrium. The scientific name of sodium is natrium. Okay, so it is highly reactive substance. It is used as a coolant in both the circuits. All right, now let's come to the next part, that is the role of the SMR, small modular reactors. So as I told you already that to go to the stage 2, we need a stage 1. Okay, now we cannot just put stage 1 reactors and stage 2 reactors very close. Okay, so we need to establish some stage 1 reactors near the stage 2 reactors, and these stage 1 reactors can be made into small modular reactors which have less power capacity and which can use uranium coming from the USA. Okay, as per the 123 agreement. This 123 agreement was signed for the delivery of the nuclear fuel from USA to India and many more countries, and this was signed in 2005. Okay, between Manmohan Singh and George Bush, I believe. Furthermore, these small modular reactors can come into the private ownerships, which India is heavily looking towards. All right. Yes, you can see here Section 123 of the US Atomic Energy Act, basically telling about the cooperation agreement for significant transfers of nuclear material or equipment from the United States. So here we are talking about the uranium itself. Alright, such agreements, commonly referred to as 123 agreements, facilitate cooperation in other areas such as the technical exchanges, scientific research, and safeguard discussions. Here you can see a picture of the 123 agreement being signed. Alright, now let's quickly talk about what is the value of stage 2 for us, for India. So the PFBR has a capacity of 500 mega electron watt. So that's a lot of energy, the PFBR. The DAE proposed building four more fast breeding reactors of 600 megawatt electron each, and two in Kalapakkam at the same sort of unit in the Tamil Nadu from 2021 and two from 2025 with sites to be selected. So Kalapakkam we can notice and highlight as the first prototype fast breeding reactor. Okay, this is PFBR. Next one will not be prototype, of course, they will just be FBR. Okay, this prototype one is 500 mega electron watt. All right, so experts have said the best way to work on stage 2 is to press reactors into commercial services. All right, now what else we see, that what is the importance, that solar electricity, the solar electricity is under 2.5 kWh, where nuclear electricity cost around as rupees 4 kilowatt hour. All right, so let's say as twice as expensive the nuclear energy, but what we see is that the nuclear thing or the nuclear energy is the way for the future. Why can we say the solar is more preferable than nuclear energy? Yes, it is more preferable, but we must also focus on the nuclear energy. Why? Because we have to reach our net zero goals by 2070 and we have to reach a renewable energy target by 2030. So this we dealt with in the last lecture. So it is very important for us to grow our nuclear development program and quickly reach the stage 3, where we'll be producing energy, nuclear energy, which may be cheaper than the solar energy produced now. All right. Second thing we see, what are the, let's say, we saw the significance in the last slide itself. Okay, solar versus nuclear, just a simple debate. Solar versus nuclear. So as we reach in stage 2 and stage 3, it will become even cheaper, and we have to do this because of our net zero goals by 2070, 50, and 30. All right, so this you can read in a different topic and manner. Now let's talk about what are the challenges of the PFBR. Okay, what are the challenges that these fast breeding reactors are, let's say, facing? So FBR are harder to handle than other reactor designs because it's a completely different designs. We have experience of the PWHR, pressurized heavy water reactors, but not PFBR right now. It uses a different coolant, different core material, and many other things are different. Okay. Second thing, that safety concerns are there. We do not have experience of handling it right now. In future we may have, and there have been disasters like the Fukushima disaster in the past, which let's say give us an eye for or the towards the safety concerns. Further, what we see that the civilian nuclear program nodal regulatory body, that is the AERB. AERB. Here we can see the AERB. It is basically under DAE, sorry, and DAE is under government. All right, so it's not a separate body which the multiple uh, international bodies, even the International Atomic Energy Agency, that is IAEA. So IAEA recommended the Indian government to set an independent statutory atomic regulator. Okay, instead of this, which is basically under the government by a few stages. Okay, we can see here that the Bhavini, which is producing the FBR, Then NPCIL, most power, UCIL and AMD uranium. Question came on this in the prelims. Okay, and the Atomic Energy Regulatory Board, AERB, which looks at this DAE. So it's under basically the DAE, and which is under the Atomic Energy Commission, which is under the government of India. Okay, so it's government owned. The regulatory thing is also the government owned, which is not liked by the IAEA, first of all. All right, let's see one more thing, that these produce lot of waste, such as the third stage thorium cycle or the stage 2 thorium cycle produces lots of waste, such as the cesium. Okay, it is radioactive cesium 137. Then there is actinium 227. There is radium 224, radium 228 also. Okay, these are all radioactive elements. These are all radioactive elements. This is all radioactive waste, the disposal of which is very hard. So this is the issue that is going in the Kundakulam in Tamil Nadu, Kundakulam nuclear plant in Tamil Nadu. Okay, so disposal of this is really hard, and we must look at this concern also. You can read about the radioactivity as a separate topic, very, very important topic. All right, so this is all about the PFWR and fast breeding reactors and so on. So this is where we end our lecture. This is Yatharth here signing off. Thank you very much for presence. If you have any doubts or any feedback, please mention it in the comment section. I will be really, really happy to help you in any sort of manner with your questions and doubts. All right. So thank you very much. I'll see you in the next lecture. Have a great day ahead. Keep studying. See you soon.